I believe today we have Thibaud on from Ateme. Is that correct?
Yeah, sorry, I was muted.
Okay.
No worries. No worries. You so you were able to attend the Mile High Video Conference, MHV 22, and had some insights to that. We'd love to actually hear, the rest of the members to hear what you both what you learned and also what you presented at the conference, because that's a nice interconnect conference for those who don't know, between sort of people doing pure video research and obviously companies that are implementing that video compression research into their services and products.
Yeah, so basically in MHV 22, we had a couple of presentation and posters. And one of the posters was specifically on sustainability in video streaming. So my proposal would be that I present to you this poster. I cannot share my screen at the moment. Okay.
Is it possible for you to give sharing to Thibaud?
Okay, I can.
Is that okay now? Yep.
Yeah, thank you very much.
No worries.
So, sorry, it's not a slide deck. It's just a poster we've presented in MHV 2022. The presentation or the topic, the presentation is entitled Sustainable OTT Video Distribution Powered by 5G Multicast Unicast Delivery and Versatile Video Coding, so VVC. So just a bit of context before presenting the poster. So this work has been achieved with several partners, Interdigital, NNC's Technologies, and IETR, which is an academic lab in France. We are all together inside a project called MS, which is standing for Energy Efficient Enhanced Media Streaming Project, which is funded by the Brittany region and Rennes Metropole, the city where the work is achieved. So that's for the context. So what's the topic of the paper? So it starts with some context aspect, introducing the use case and the requirements for it. So the first element of context is the situation of operators today when they want to introduce, new video services. So they have to deal with potentially multiple networks to be addressed, multiple headends to be deployed, multiple devices to be addressed as well. For an operator, it means that there are a lot of redundancies in all of that, whether it is in the video services fabrication, in the delivery, because of all of the networks, in terms of CDN, in terms of video stream to be packaged in multiple formats, etc. So it's a lot of redundancy, and actually redundancy is often connected to a waste of resources, computational power, energy, etc. So that's the first element of context. The second one is here on the right side, is what we all know. It is that video traffic is skyrocketing at the moment. So we all know this famous Cisco report we are all citing in all our papers, but the reality is that in 2021, 59% of the mobile traffic was video, which involves a huge pressure on the network and a huge energy consumption. Because on that mobile video delivery chain, what is distributed in the physical layer is a large portion of the energy associated to a video service. So to address this video traffic peak, we need some tools to reduce energy while keeping an high quality of experience, because it's what operator wants. At the end of the day, they still want to deliver the highest possible quality. So in the project, we've tried to translate those context elements into requirements that would help streaming to go toward a sustainable approach. And it's what's explained here in this section 3. So we just set a couple of requirements we will try to address. First one is that the operator wants to be able to monitor the energy consumption of its video services. So it means data center, of course. It means also network, all of the delivery chain. Second requirement we add in that case, we want to remove as much as possible the redundancies that are brought by massive unicasting over the network, which is a waste of bandwidth, especially for live services, of course. We want the end user to be able to lower its energy impact if he wants to. And we want, of course, the bitrate of the video services to be minimized as much as possible while maintaining the expected quality of experience. So that's for the context of this work, of this project. And what we have proposed to address all these requirements is a framework that is addressing the requirements I was just talking about. So here is a framework. It is composed by 3 parts: the head-end part, the delivery part, and the player part. On the head-end part, we are introducing several new technologies that bring functionality, which at the end of the day enables energy saving, whether it is on the network, on the device, on the display. So first is some pre-processing technologies, which in this project are brought by InterDigital. There are 2 specific pre-processing that are involved here. First, a content mapping using SLHDR or CTI-SCI message for VVC. Basically, it enables to adapt the brightness of a signal to the brightness of the display. So it means that if you want to lower the brightness of your display for energy purpose, you can have the appropriate post-processing that enable to maintain the quality at the meantime. Second aspect in pre-processing, the artifact masking using film grain synthesis or FGS with VVC still. I will talk a bit about that later. And of course, what is brought by Ateme, the video encoding and the packaging, leveraging the recently standardized versatile video coding that is implemented in our real-time encoder, combined with CMAF, low latency packaging, enabling to remove many OTT redundancies in the packaging, let's say. We also introduce green Mpeg metadata generation in the head-end, which is a standard developed by Mpeg, which enables to carry metadata together with the streams to tell the decoder a complexity information about the streams. And we also introduce some energy reporting XML file in the Dash manifest in order to give the players the opportunity to have access to the complete end-to-end energy consumption in the chain. So that's for the head-end. On the delivery side, to address those requirements, we mainly leveraging 5G media streaming for efficient unicast over 5G network. And when necessary, we are using a multicast broadcast service, which is a Release 17 feature, which is brought by NNCs in this project. So the idea is that on your physical layer, when the audience is high, instead of having a massive unicast, a massive parallel unicasting of the same service, you switch to multicast to save a lot of energy on the physical layer, on the emission side. And finally, we've implemented some functionality at the player side. So to enable VVC playback on device, the IETR in our project developed a VVC live decoding libraries, which is capable of running on ARM platform in, let's say, an optimized manner. So of course, it's less energy-wise, it's less optimal than a hardware chipset, but it's VVC. It's like a really recent standard. So that's what we have at the moment. We've implemented the post-processing that came with this pre-processing, and we have implemented a reporting green metadata reporting for the end user, which enables to indicate to a user for given representation what's the impact. In terms of energy saving, so that's so it's a bit, as we know here, it's a bit tricky to measure the energy saving because it's not only kilowatt-hour, there are also other aspects involved. But anyway, we've tried to evaluate that on all the framework that we've proposed. For video coding, a live VVC is around, or live VVC is, let's say, around -15% bandwidth saving over HEVC. It means that on a regular 1080p service, you save from 37 to 75 kilowatt-hour, depending on the energy per bit estimation you are using. And of course, it scales on the full ladder if you introduce, intermediate resolutions. For content mapping and FGS, it's still further bitrate saving that you can add on top of that, so a few kilowatt-hour on top of it. The technology for display optimization has been evaluated by Interdigital here in the project. The brightness reduction that is possible with SLHDR or CTI for VVC indicates that if you lower the brightness of the content, so of course you lower the energy consumption of a mobile device, because a lot of in a mobile device, a large portion of the energy is concentrated in the display and the modem. So if you save a bit of brightness while maintaining the quality of experience, you save a significant amount of energy. And so yeah, that's it for the display optimization brought by Interdigital. On the transmission side, so I am not an expert of transmission because at Ateme we are more video, at least me, I'm more a video compression guy. But what NNCs did on this work is simulate and estimate the threshold from which you can gain energy on the physical layer while switching from Unicast to Multicast in the context of a single frequency network, a mobile single frequency network. The simulation achieved by NNCs indicates that even from one user per cell, it sounds counterintuitive, but it's the case because as long as you have one user per cell that is accessing a given content, if you switch to multicast, you benefit from SFN, and you save overall bandwidth. So that's for the transition. So for your information, so following our previous one of our previous discussion we had in the lexicon working group, I've contacted NNCs and they agreed to present like this part about energy and multicast in an upcoming meeting. If we want to invite them, I don't know if it will be done or not, but anyway, they are willing to present their result and to,
yes, I think it would be very useful for group one. So yes, let's follow up on this for sure.
So to be continued. And as a conclusion on future work, so basically here in this MH presentation, we have proposed an initial framework toward sustainable delivery for video streaming. We are leveraging advanced compression with VVC. We try to introduce pre and post-processing technologies that enables indirectly to optimize energy in the device. We have introduced the standardized green Mpeg metadata that are not really used in our framework at the moment, just for profiling purpose, but in our future work, we would like to exploit that further. So that's the presentation I had today. So of course, at Ateme, we are working on optimizing energy for encoding for CPU on server platform, but we are also looking into those aspects of using new technologies to have impact everywhere in the chain, not only kilowatt-hour in the server. So that's all I have for today. Thank you. If you have any question.
Yeah, Thibaud, it's Tim Siglin. I've got two quick questions.
Yeah.
One, when you talk about this display optimization where you're reducing from 1,000 to 750 nits, was that a comparison of VVC versus HEVC, or just using
no, for this one is the particular impact of the pre-processing content mapping that is introduced by Interdigital here. So the idea is that you deliver your video services. It's independent from the codec. It could be done, for instance, with HEVC. But let's say you have your video services, you deliver it, and together with the services, you deliver metadata or side information that enable any receiver to adapt the content to the display or to a lower brightness than the native brightness of the content. So it means that if in a device you want to lower the brightness for energy saving purpose, you will bring together with that the appropriate processing that would map the content to this lower brightness, and that will preserve video quality in the meantime.
Okay, thank you for that clarification. And then Ariane had put a message in the chat that said the 15% savings that's listed for HEVC is less than promised by the standards group itself.
Yeah. So of course VVC is so in standardization, you are using a reference software implementation to evaluate the performance of the standard. So at the moment, VVC, of course, is supposed to bring a 45% saving over HEVC, but that's like the final result you will get. When, as an encoder manufacturer, you're starting implementing the standard and you want to keep it real time at the meantime, you introduce coding tool in a progressive manner.
Right.
So at the moment, what we have in real-time profile are in this range of performance, but as for HEVC or AVC before, the encoder manufacturer roadmap is supposed to progressively increase this performance to ever reach the full potential of
and I know with AVC, at least in the video streaming world, I come out of video conferencing, so we had used AVC for quite some time prior to that. In the streaming world, it took us about 10 years to get to sort of that 50% optimization. HEVC seemed to get it there in about 6 years. Do we think with VVC we'll get to that 45% in the next 3 to 5, or it'll be a bit longer than that?
Oh, I think it should follow the similar progression curve we had for previous codec.
Okay.
So VVC is more demanding complexity-wise, but the CPU are more powerful. So it's a kind of Moore law kind of approach. So you get more computational power, so you can increase the compression gain, and you eventually reach the standard target. But yeah, I would say in 3 to 5 years, this figure should be way higher.
Okay, great. Anyone else have any other questions?
Yes, I have one. Do you also measure the power usage of the decoding devices, and do you see a difference when you are running at, say, standard frame rates or half the frame rate?
So that's a good question. So in terms of, in this project, what we had access to was a software decoder, optimized for ARM platform for mobile, but still a software decoder. So of course it consumes way more energy than an hardware chipset.
Sure.
But in terms of measurement on the platform, what we have just measured is the impact of the software, decoding software that was running on the CPU. We didn't measure impact on display aspects because the platform on which we were doing the evaluation didn't give us like the tools to access display information in an accurate manner. Maybe it's not clear, but we didn't add those advanced results, and that's also what we want to do in the next step of this work, like going deeper into measurements, evaluation. But it's a bit tricky. Sorry, I don't have a clear answer for that, but
no, because I can imagine that if your silicon decodes at say 25 frames per second or even less instead of 50 frames per second, you need less power in your decoder device, in your SoC.
Okay, I understand. Okay, I misunderstood the question at the beginning. So on the impact of the frame rate, so on software decoding, the impact is huge, definitively. On hardware decoding, my understanding is that the power that is consumed by the hardware unit responsible for the decoding is not changing that much.
Right.
Okay.
That's my understanding.
All right.
We've seen that in our research in our lab as well, as that hardware decodes because you have to ultimately, power the chip up and have it ready to decode at any point. You might see a 2 or 3% reduction, but nothing significant.
Okay. Yeah. All right. Because suppose it was of some significance, one could also then in for sure closed networks, which devices are watching content. You can have then also estimates if you change over the bitrate at your encoding, depending on your decoders, what will happen with the total energy consumption. So a bit of holistic, energy-aware encoding for the end-to-end chain.
Yeah, it depends what driver you want for your encoder. If you're aware of the device, of the audience at each instant in time, you can drive your encoder and packager accordingly. So far, it's tricky to do, but that's for sure promising.
Yeah, well, give or take a couple of years, things are All right.
Yeah, that's analytics-driven encoding is something we are looking at, but it's like a wide.
It's
well, thank you. Thank you, Thibaud, for spending the time to do this. Clearly, this is of interest to several of us on the members meeting today, and I believe Adam will take this, turn it into